Great. Good morning and welcome to the morning session. It's a great pleasure to have Ashvin Vishwanath from Harvard University, and he's going to tell us about using measurements to sculpt entanglement to create non-abelian topological order on quantum hardware. Ashvin, please take it away.
Okay, so thank you very much, Onkar and Rajesh and everyone who helped make this visit possible. I had some last minute schedule change and they were very accommodating. Made it possible for me to give this talk. So I've been looking at my talks, and I think every year I've been coming and giving a talk at ICTS. So great pleasure to be back here. I try to think of a topic that would fit with this set of lectures that Tadashi is giving, including connections to entanglement. So let me tell you about this work. It's really maybe a cross-disciplinary, the most cross-disciplinary thing I've worked on. So you'll see that it has, connections to, creating kinds of quantum entanglement in a many-body system. So as far as I know, it has no gravitational analog, but we'll talk about entanglement. We'll also talk about these very interesting quantum states of matter, simple but very interesting quantum state of matter called non-abelian topological order. And finally, I'll talk about how to realize this on an actual quantum machine on these newly available quantum computers. And one of the aspects of this work that's very interesting for me and very sort of novel was the fact that we actually use measurements. Okay, so measurement is something we hear about when we first learn quantum mechanics, how counterintuitive it is, this and that, but we don't really return to that when we actually utilize quantum mechanics. But here there'll be an instance where this will play a central role. We'll actually use quantum mechanics, the measurement in quantum mechanics, to create the states that we are trying to target. Okay, so in contrast to measurement in other branches where you use measurement to extract information, we know in quantum mechanics it can actually change the state. And you can use measurement as a way to sculpt the state of matter and finally get to the point that you intended to begin with. That's kind of the strategy we'll adopt. Okay, so these are my collaborators. So Nat was a student at Harvard, and now he's moved to Caltech, and he's moving to Stony Brook for a faculty position. Ruben is a postdoc, now moving to a faculty position in Chicago, and Ryan was also a postdoc at Harvard, now at UCLA. So we had these theoretical ideas, but they got much more interesting when we collaborated with this quantum computing firm, a very unusual quantum computing firm. These two people were our main contact, and they were really interested in doing science. And somehow their bosses never found out, and we could have this great collaboration. Okay, so this is an outline. So there are different, as you can see, there are different parts to this talk, different things that have to come together. I'll start by talking about quantum phases of matter. What happens when you have many, many quantum particles coming together? In particular, these class of phases of matter, topological orders, and a subset of them which have non-abelian anyons. Okay, so that'll be part of the introduction. Then I'll talk about how you can prepare quantum states with measurement, and then we'll go to these experimental realizations, and finally some generalizations in the discussion. Okay, so I'm sure people here have a different background, so feel free to interrupt anytime with questions. It'll also help me to know what is going across and what is not. Okay, so when we think about quantum phases of matter, so we're really thinking of a many-body system. Okay, matter is just in this context is just talking about many-body system. And the intrinsic degrees of freedom are all quantum mechanical, of course. And the big question in condensed matter physics, in a way also in field theory, I think, is what happens when you have these many, many degrees of, quantum degrees of freedom? What are the new emergent properties that you can get? And here are a subset, one of the things we understand very well is spontaneously broken symmetries. There are other phases which do not break symmetries, which are relatively simple to describe. The so-called invertible topological phases. Example is the integer quantum Hall effect. But for this talk, I'll be mainly interested in this bottom part, which we will call intrinsic topological order. So this word topological is highly overused, but there's a very specific definition to this term, and we'll talk about that. And they are realized in the fractional quantum Hall effect. Okay, so these theoretical ideas actually have met experimental realization. Yeah, and we'll be interested in creating these kind of states and a particular subset that I'll talk more about. Okay, so what are the characteristics of these different quantum phases? If you have spontaneously broken symmetry, the characteristic is an order parameter. Okay, so this is famous experiment on the Bose-Einstein condensates. They have an order parameter. You have these particles, bosons, that all condense into the same quantum state. Okay, the Q equal to zero momentum, or the single particle ground state. You have many of these particles taking up that state. That's why it's called a condensate. Okay, so we'll use the word condensation in some generalized sense when the ground state is full of these, this occupation of a particular state. Yeah, and there's a very simple local order parameter that is defined that fully characterizes that state. Yeah, these other phases have more subtle signatures. For example, these invertible topological phases are typically associated with edge states. The bulk is not particularly interesting, but at the edge there are low energy excitations that are interesting. But these topologically ordered phases, they are also gapped in the bulk. There's a minimum energy you have to pay to make excitations. But when you make those excitations, they have very unusual characteristics. Okay, for instance, they have anyonic statistics. So we'll be talking about 2+1 dimensional systems. You take one of these particles around another, they can obtain a non-trivial phase. Even as self-statistics, they can have statistics that are different from those of bosons and fermions. Okay, so they have anyon excitations in the bulk. That's really the characteristic of these topologically ordered phases. Okay, so in a way, they're very simple. They're gapped. Okay, so if you think about a quantum field theory describing them, the quantum field theory has no states. For example, if you put it on a sphere, but if you put it on a manifold, a different manifold like a torus, then they have some non-trivial degeneracy, but it's still just finite. So it reduces to a quantum mechanics problem, but which quantum mechanics problem you get, and the details are highly non-trivial, and the excitations, if you go above the ground state, the excitations have all of these interesting properties. Okay, so we'll be interested in these kind of states. Okay, so just to give you a little more of contrast between these two families of states, symmetry breaking, an example is just the Ising model, or a magnet, if you like. The spin can point up or down. The ground state, if you like, this is fully symmetric. It still preserves the symmetry, but it's a superposition of all up and all down. Okay, that's like the condensate that we've been talking about. And this is also in the quantum information context, Schrödinger cat state, or a GHZ state. This combination is very sensitive to decoherence. Okay, so this can talk to the environment. The environment can distinguish the all up and the all down state, and this relative phase is typically very hard to control. Okay, so it's easy to measure the order simply because it couples so well to the environment, but at the same time, this relative phase is very sensitive to decoherence. Okay, so again, in the quantum mechanical context, people try to use this GHZ state, this kind of a Schrödinger cat state, as a very sensitive detector. It allows you to go beyond the standard quantum limit. Okay, now, in contrast, this topological order that we'll be interested in can be, if you want a simple physical picture, at least in some instances, you can think of it as a loop condensate. Okay, there is some microscopic degree of freedom giving you loops. You can think of these loops as electric field lines or magnetic field lines. And the ground state is sort of a uniform quantum superposition of all of these loops, but there is no local order parameter that allows you to tell that you're in this phase. Okay, so from the gauge theory perspective, these can be thought of as deconfined phases of gauge theories. And one of the interesting things is that simply because it's hard to sort of characterize this order, you can actually use it to hide quantum information from the environment. Okay, so although we can use the same words, condensation, for both this particle condensate and loop condensate, the physical manifestation couldn't be more different. Here you're very sensitive to decoherence, but over here you can actually use the subtle nature of this order to hide quantum information from the environment.
Just a very dumb question, but in this setup on the right, the true degrees of freedom live on those lattice points that are shown, right?
Yeah.
And so when you say psi is sum of loops, you mean that there's another representation of the Hilbert space which involves loops that have condensed, or I mean, is that a precise equation, or is that, yeah?
I'll be a little more precise. So I think the next couple of slides, I'll tell you exactly what these loops are. Yeah, so ultimately everything will be built out of qubits, and the loops will come out of that.
When you say hide, you'll be more precise about that also?
Yes.
What exactly that means?
Yes, yeah. I could maybe say a couple of words right here. So we talked about this ground state degeneracy on the torus. So you could think of those degenerate states as being your qubits. And then you can ask, are those qubits susceptible to decoherence in the same way that a microscopic qubit would be? So those different ground states actually correspond to different loop configurations. For instance, it could be whether you have an even or odd number of these loops around the non-trivial cycles of the torus. And it's impossible to know that unless you have a global view of the entire system to be able to count the parity of loops that are spanning the torus. So in that sense, the qubit, whether it's in 0 or 1, that information is very non-local. It's distributed over the entire system. So the typical environment that is not designed to look for that will not be able to distinguish 0 and 1. And so it won't be able to apply a random phase between the two, or will not be able to shift the energy of the two relative to one another. So that is the basis of this quantum memories that are topologically protected. You kind of engineer your quantum system so that it's very hard for the environment to tell. Now, it's also hard for you to manipulate the qubits because they're non-local, but you can design your unitaries better than the environment will, the random environment will do that. So there is a gain. So all of the current approaches to quantum error correction in some sense utilize this approach. So there are error correcting codes, but if you look at them more carefully, they somehow can be reduced to this kind of physics. Yeah, so the last point, again, I'll say this in a little more detail. You have these loops, and the ground state is all closed loops, but you can break them. When you break them, you get endpoints, and those endpoints are going to be these particles, these anyons. If you think of these as electric field lines, these are really the charges in your theory. And those excitations have interesting properties. And that's sort of a simulation of this ground state wave function. We'll come back to what these loops are made of. But if you think of the wave function, the quantum superposition as being a movie where you go through the different instances, the ground state is some loop condensate of this kind. Okay, so so in terms of realization, that's something, of course, we are very interested in. How do you realize this in an actual physical system? In fact, people have already realized these kind of states, these anyons, in actual quantum mechanical systems. And the first place it was realized is in the quantum Hall effect since the 80s. So it's not new, but there's been a recent explosion of new platforms where they've been realized. Again, very recently, last year, people have found a way to realize the same states as in the quantum Hall effect, but without applying a very strong magnetic field. You can switch off magnetic fields, much easier to do, and realize these kind of fractional or any fractional states with anyons. Okay, so you can think of this as inhabiting some particular territory in this range of length scales, if you like, and how much control you have over the system. These quantum Hall systems, or these so-called Mori systems, have typical lattice spacings of tens of nanometers. So this is an order of magnitude or 2 orders of magnitude bigger than the atomic spacing. That's something like 0.1 nanometers. but you have a fair degree of control because it's somewhat bigger. You can apply strong fields which are at the same length scale as these structures, and you can control many things like the density of electrons simply by changing a voltage. Okay? And when you're at the atomic scale, you cannot really change the density of electrons. The only way to do that is by changing the chemistry of the system, which is notoriously hard. The traditional place we have worked in condensed matter is down here, the atomic scales. Again, there are states that have been proposed that have anyons, also called quantum spin liquids, but they've been very hard to realize in experiments. And if they've been realized, it's very hard to know for sure, precisely because the signatures of these quantum spin liquids or these topologically ordered phases is very subtle. And you have much less control. You're kind of at the mercy of chemistry if you want to change the properties of these systems. Yeah, but recently we have gotten a new kind of part of this graph, which is you go to much bigger scale. So really they're micrometer scale, separated quantum bits, quantum degrees of freedom, but you have a lot more control. And these are really these quantum platforms. They can take many the building blocks could be of a variety of systems. They could be superconducting quantum bits. They could be atoms. They could be ions. I'll talk about a platform which involves ions because they're electrically charged. They're easy to move around. They have a quantum degree of freedom, and you can do very precise quantum operations on them. And I'll tell you the idea over here will be about how we created these non-abelian topological phases in one of these quantum devices, okay, using measurement as one of the inputs. Okay, so again, a little more about distinguishing quantum phases because this kind of comes up when we come to these quantum platforms. We talked about these different states of matter. And when you think about these kind of electronic systems where you cool to very low temperatures, it's quite clear what you mean by a quantum phase of matter. Okay, you would like to go to zero temperature. Of course, you cannot really do that. But you're cold enough if your temperature is much smaller than the gap. You're talking about these gapless phases. You cool the system to temperatures that are, say, an order of magnitude smaller than the gap. You're effectively in the ground state, okay, for all practical purposes. And now, as you change parameters, you could go from one phase to another. And they're different if you always have to encounter a phase transition. Something singular happens. Although you change parameters in a continuous way, there is a sudden change in the properties of your system, or you go through some gapless region. Okay, the energy gap closes and then reopens. That's how you can distinguish different phases. It's a little bit more complicated for these quantum platforms because we don't quite have a notion of temperature. Okay, so you have a lot of control, so you have a lot of information about your system. You're not quite in the thermodynamic limit. And you can ask, what is the distinction between quantum phases? Okay, what is the analog of having phase one and phase two? What is the analog of gapless? And here, this is really where entanglement comes to your rescue. You can think about short-range entangled and long-range entangled phases. What is the quality of entanglement? And this can help you distinguish different phases. Okay, so instead of looking at excitations as we do over here, or looking at ground state energy, you really look at the level of wave functions, the structure of the wave function, and how they are different.
Sorry, what did you mean when you said that they're not quite in the thermodynamic limit? Because I thought these are much bigger systems than the other ones.
So sorry, when I was showing the scales, they are really the separation between the qubits. And then it's a question of how many qubits you have. And here the kind of numbers we'll talk about are dozens or maybe 100. And you have control over all of them. So usually in thermodynamics, we say we can control the temperature or the chemical potential, but we cannot control the individual motion of the particles. But here you have control at the single quantum bit level. Yeah, there's a question back there.
But are the error correction properties protected against these small temperature fluctuations?
Yeah, that's a very good question. So there is something called, which in the, when people try to make these topological quantum bits using, by actually making a state of matter, then even if you're at low temperature, you have a finite density of quasi-particle excitations. They're exponentially small, but it's not zero. And they will set a time. It's called the quasi-particle poisoning time. They kind of poison the topologically protected operations that you have. And they will kind of limit how long you can take before you complete your computation. So that actually sets the lifetime of your quantum bits, if you like. Even the protected quantum bits. Of course, this is going to be much longer, hopefully, than what you would have had if you didn't do that, if you didn't actually get the topological bits, but it's still finite. So then you need another layer of actually active error correction. And so the rough roadmap people have in their minds is, if you were to go with these topologically protected quantum bits in some quantum Hall system, let's say, that'll give you quantum bits with fairly long lifetime, and then you have to do less error correction. So yeah, but I think a lot of it is has to do with trade-offs, right? It may be easier to do error correction rather than get that extra factor of 2 in cooling. But yeah, that's a good point. It's never really zero temperature, and you've got to worry about that. Okay, so one of the analogs of these different phases of matter is whether if I give you a particular quantum state, let's say on one of these devices, and I ask you, is it different from another quantum state? You can ask the question, can I convert one into the other by applying a unitary quantum circuit? And in addition, we'll ask that these unitary operators are local in the sense that they only act on a finite number of quantum bits in every layer. Okay, so there's a layer that's composed of these brick walls. So this brick wall is really some unitary operation acting here on these 4 quantum bits and gives me these output 4 quantum bits. Okay, so if I make a quantum circuit of this kind and sort of have this depth, these are acting now on, so in a single layer, I don't have overlapping unitary circuits, and I kind of expand that out into different layers. The question will be about the depth of this quantum circuit relative to the number of qubits that you have. Okay, so there's a scaling over there, and when this quantum circuit is deep, we think of the 2 states over there as actually being in different phases of matter. Okay, you can talk about exactly how deep. The standard the standard metric is, if you have linear depth, you can pretty much create any of these gapped quantum states. Okay, so linear depth is really a sign that you're talking about different quantum states. Okay, so there's an analog of this kind of going through a gapless phase is a bit like using a linear depth quantum circuit.
Going through a gapless phase is like having a state which has long range entanglement.
Yes.
And so why is linear depth related to taking away functions with long range entanglement and then short range again to the mind?
Yeah. So the question is, how do you relate the gaplessness to the fact that it's linear depth? So one of the things that you see just from the fact that it's linear depth is, there's this Lieb-Robinson bound on the spreading of entanglement. And by having linear depth, you ensure that that bound is not constraining you. Right, so the quantum information here can travel to any other part of the system. That wasn't a question, I think, right, yeah. So you can see that linear depth is, it feels sufficient. Another thing is that we'll talk about the story code, the state we had before. You can show that you need linear depth. If you want to start with the product state, to create that, you need linear depth circuit, if it is local unitary circuit. And one of the interesting questions is, if you're allowed to relax these conditions, locality, unitarity, and so on, can you beat this linear depth? Can you prepare things faster? And we'll see that if you include measurement, you can.
If you're allowed to beat locality, surely you can prepare it in one go, right? If you just act with arbitrary unitary, I can do whatever I like in one layer, right?
Yeah, so locality may have different meanings. So for example, you could say, I'm going to give you a unitary circuit that can only take 2 legs as inputs.
Right, that's what I would say as locality, right?
Okay, so that is locality at the operator level. But where are the inputs of these 2 legs? Do they have to be spatially next to each other? Or could they be in any part of the system? So you have spatial locality, and then you have sort of operator locality, like K locality.
I see.
You're right. If you, so the first restriction is you have operator locality, so only 2 legs, but they could be anywhere. Can you prepare, for example, the toric code with that? You cannot. Now, of course, if you give me the general unitary, which allows all of these things as inputs, then you can create anything. Yeah. Yeah.
Okay, so I was wondering what kind of unitaries are considered here? Is it like all possible k-local unitary? Or like if you restrict to, let's say, Clifford gates, does it still able to relate all the gap phases?
So Clifford gates definitely are not able to relate all the gap phases. Are not. They are not sufficient, yeah. In fact, to prepare these non-abelian states that I'll talk about, you explicitly have to have a non-Clifford gate in your protocol. But we can always think of these as there's single qubit unitaries and 2 qubit unitaries that end up making a universal set. We don't have to go beyond that. We can just have more layers.
And here, it is essential to consider local unitary, not the local operation, including measurements.
Yeah, for this result, yes, we're talking about unitaries. This is at the level of unitaries, coherent preparation of states. These are the demarcations that you get. Now, as you change those resources, some of these demarcations can disappear.
Thank you.
There's another demarcation that people like to think about, which is instead of unitaries, think about Hamiltonian evolution. So think of evolving these qubits with the Hamiltonian for a small amount of time. Now, roughly speaking, these are the same, having unitary operation of this kind and Hamiltonians. But the Hamiltonians have tails. They're exponentially small, but there are these tails. And that can also give you distinctions between phases. So this is sort of, you've got to take this with a grain of salt. We are trying to mimic the Hamiltonian evolution over here by using these quantum circuits. This is a very stringent kind of restriction to what kind of unitary operators you can apply. So 2 states that are really different over here are definitely different over here. But you can have states that are, we think of as the same over here, but are actually different at this, with this more strict definition of what can be connected. But we'll be mainly interested in states that are very different, like the product state and the toric code. So using this more stringent definition is fine. Okay, so to connect again to entanglement, actually I'll need a couple of slides for that. So let me talk about the question that Suvrat raised. What are these loops made of? Okay, so ultimately we have just qubits, just quantum spins. Imagine that they're decorated on the links of the lattice. They can be up or down, and when they are, pick something. Let's say when they are down, the sigma z is, let's say, -1. And I apply a constraint that, it could be an energetic term, but ultimately it's a constraint that the product of sigma z on this cross term is always 1. Okay, so you should be able to recognize some form of the Gauss law over there. And when you do this, you ensure that a loop that is defined as going through all the bonds with the downspin, those loops will always be closed. Okay, so as soon as you apply this constraint, the set of states that you're talking about are closed loops. Okay, and then we can introduce some sort of quantum dynamics within the subspace. And that quantum dynamics could be this product of X around a plaquette that will simply flip all of these spins in a single plaquette. But even after you apply this operator, you can check that the constraint is still maintained. So if you like, this quantum dynamics commutes with this constraint. Okay, so in that way, you can move around this manifold where you have closed loops. And if you pick your quantum dynamics correctly, like this one over here, it'll explore the entire manifold and give you a ground state wave function that is an equal superposition of all of the closed loops. Okay, so you can see that although this is a loop wave function, it's ultimately coming out of quantum spins. And the Gauss law is also applied as some term in the Hamiltonian, and the superposition term is kind of like a B squared term. And you could also add the E squared term if you like, but yeah.
I have one question. I mean, this is an Ising model that you are looking at?
Yes.
Ordinary Ising model and sort of rewriting it in terms of new variables.
So, when you say Ising model, there are 2 things to it. One is the Hilbert space. The Hilbert space is the same as the Ising model.
Okay.
On
interaction.
But the interactions are not the standard Ising model interactions. Yeah. Okay. So it's a different model compared to the Ising model in that sense. Usually in the Ising model, you just have product of two spins. And then you may have a transverse magnetic field like a sigma x. Yeah, here we have these 4 spin operators. Product of 4 spins, that's what is giving you the constraint, if you like, closed loop constraint, and then another one which is flipping within this, this manifold. Okay, so this is really an Ising gauge theory. If you were to think of this as a constraint, it's an Ising gauge theory, a pure Ising gauge theory. But one of the nice things that Kitaev did, it's a very small change. He just put everything in the Hamiltonian. And instead of saying something is a constraint and something is the quantum dynamics, he just put everything in the Hamiltonian. The advantage is that now you have a plain vanilla quantum spin model. There's no constraint. The Hilbert space is really a product Hilbert space. If you go to low energies, you go to the ground state, this behaves like a constraint because violating it gives you no advantage. It commutes with the other term. So you're guaranteed that the ground state will be where these terms are exactly equal to +1. So yeah, you just go to low. So this deconfinement that you get is, all of this physics is just in some model which has nothing special about it. It's just a spin model where I decide to choose these as my interaction terms. So it's really an emergent gauge theory. You have none of the gauge structure at high in the UV, but at low energies, if you want to make life simple for yourself, you can think of it as a gauge theory.
To understand, what that really means is that sigma 1, sigma 2, sigma 3, sigma 4 is 1. That's what you mean.
Yes, the product is 1. Yeah,
product of all
yeah, that's what I meant. Yeah, yeah, the product of these 4 sigma z's is equal to 1. That is what will minimize the energy. So you can do that by having all of them +1, 2 of them minus, 2 of them +1, and all of them minus, right? And they all correspond to loops that just go through, that don't end. If you had a defect like this product equal to -1, so an odd number of these sigma z's being -1, let's say one is minus and the others are plus, that means the loop ended over there. And then you're going to pay an energy cost, which is this term over here, so it's an excitation. But what is that excitation? It's really the endpoint of a loop. And we'll see that that is actually an anyon. It has fractional statistics and it has interesting properties. But if you have the gauge theory perspective, if you like, this is really a charged particle. It's the source of these lines, which are really electric field lines. And there will be a dual, which is the excitation of this plaquette, which is like the magnetic flux. And you take one around the other, you get a Bayes phase, or no Bohm phase. Okay, so that's really the simplest example of a...
this is maybe a vague question. Usually we don't try to impose the constraint approximately. If you thought of something that was approximately gauge invariant, we'd kind of be in a quantum field theory, we'd be in trouble, right? Because there'd be an additional degree of freedom, which would be strongly coupled. Because, that's... So approximate gauge invariance somehow is not the same as gauge invariance. But here you're saying the physics works out that it really is a gauge theory.
Yeah, so there are many things that can be said about that. So when you talk about gauge theory, you can have a pure gauge theory with no matter, and then you can have gauge theories with matter. Now, when you have a gauge theory with matter, it's not clear whether the constraint, whether that divergency is the number of particles, the charge density. That constraint is really some reflection of redundancy, right? Instead of talking about particles, you can just talk about the electromagnetic field and say every time I have this defect, I'll call it a particle. So the thing that is special is the pure gauge theory. So divergency is 0 everywhere. That is very special. That is a Hilbert space that is constrained. It's not a product Hilbert space. So a lot of the intuition we have for quantum mechanical systems breaks down for these pure gauge theories, including things like entanglement entropy and stuff like that. So the nice thing about thinking of this model, which is just a plain vanilla spin model, is that the low energy physics looks like a gauge theory. But if you start heating up the system, it does not look like a pure gauge theory. You'll start seeing matter fields. You can maybe rewrite it as a gauge theory with propagating matter fields, which is more generic. There are no constraints in the usual sense. But there may be even distinctions compared to that if you go to the boundary. So yeah, there are many levels of subtlety over here. But the low energy physics over here, if you just think of some microorganism living here that lives at very low temperatures and is trying to do experiments, it'll think it has a gauge theory. it'll be indistinguishable from a gauge theory. Yeah.
So, as long as this first term exists, it is, I mean, with this negative coefficient, this is always the ground state.
So yeah, if you want to get this particular quantum superposition as the ground state, you need a negative coefficient for this term and a negative coefficient for that term on every single bond, every single plaquette and every single site.
Thank you.
Okay, so roughly speaking, this is kind of the sketch of the wave function. Any loop, the vacuum, any loop, this is the quantum superposition. And if you have the endpoints, these turn out to be anyons, these abelian anyons. Okay, so now let me make a connection to entanglement. If I give you a wave function and I ask you, are you in this topologically ordered phase? And the ground state wave function has no excitation, so you can't go and look at the statistics of the excitations. So what can you do to tell which phase of matter you're in? Are you in a trivial phase of matter? For example, just product state. All of the spins are just in some particular state. Or are you in this non-trivial state with these closed loop condensate? Well, one way to do that is to look at the entanglement entropy. You take, subdivide your region A and B. You look at the entanglement entropy of the subregion A in the ground state. And it has an area law. The entanglement scales with the perimeter of the system. But it turns out that there's an additional contribution, the so-called topological entanglement entropy. The important thing is that it's negative. It lowers the entropy. And it's actually universal. It only depends on a certain feature of the topological order, the so-called total quantum dimension of this topological order. Okay, so for simple abelian states, this is just related to the number of ground states you get when you're on the torus. Yeah, good question. Yeah, let me just, I'll try to explain it over here. So for the Z2 toric code, this thing is exactly 1 bit of information. Okay, so it's log 2. Okay, so why do you get this reduction by log 2 for the Z2 toric code? So at the hand waving level, it is because your, the loops are always closed. Okay, so the loops have a Z2 character, and they're either there or they're not there, and they are always closed. They satisfy like a Z2 version of the Gauss law. Electric field lines are always closed. So the reason you get this topological, the reason you get this entanglement entropy, is because when you take these different components of the wave function, you have different numbers of the electric field lines entering and exiting this region. Okay, so so that gives you this the different configurations, gives you the entropy. And entropy, one way to think of entropy is really the degree of your ignorance and your the number of states that appear in this reduced density matrix. They scale with the perimeter of your system. Okay, but actually you are not as ignorant as you think you are, because these loops are always closed. Okay, so you have 1 bit of information that, every time electric field line enters your region, you know for sure that it's going to exit. Okay, so you have 1 constraint or 1 bit of information more than a completely random configuration of these loops. And that is really this 1 bit of information reduction from the area law. It's because you have a little more information than you think. Okay, so this is a very hard thing to measure experimentally. What you need to do is you need to first measure entanglement entropy. That is already hard. Then you need to find a subleading scaling term in the entanglement entropy. Okay, so I thought it was going to be, nobody's ever going to do it in an experiment. Yeah.
Based on the argument you gave, we expect it to be negative in gauge theories because we would generically expect some area law and a constant term in a generic quantum
in
theory.
the deconfined phase. So this argument I gave doesn't quite tell you why it should be deconfined. But you need this loop soup. You cannot have the loops being very small. So that's like the confined phase. If there's a large string tension for the electric field lines, they're just small bubbles of them. That's not good enough. You need that quantum superposition of all of these loops. And yeah, the Gauss law will end up giving you this. Yeah, but there's a recent experiment that actually measured this topological entanglement entropy. I'll refer again to this particular experiment. They created a small patch of the toric code. Then they could measure the entanglement entropy, and then by taking different sizes and making subtractions, you can isolate this constant part. Okay, so just one more word of introduction before I continue, these abelian anyons which have this kind of a non-trivial phase, for example, in the toric code, it turns out you have the endpoint of these strings, we'll call them E particles. Then you have fluxes where you violate the plaquette kind of term. And the two of them, they have a mutual statistics. You take one around the other, you get a minus sign. Okay, that's the best you can do in an Ising gauge theory. The magnetic flux is either 0 or pi, charge is either 0 or 1. You take one around the other, you get a minus sign. It turns out another thing you can do is to take two of these particles, an E and an M, and fuse them together. And you can argue that this, the outcome is actually a fermion. So there's a third non-trivial particle, a dion, if you like, a composite of a flux and a charge, which has new statistics, which is fermionic. And all of them, take one around the other, you get this relative phase. Okay, so this abelian, we call these abelian anyons because you take one around the other, you get a phase, and that's an abelian phase. You can think of all of them as some sort of charge flux composites. Okay, it's really the Aronoff-Bohm effect in this emergent abelian gauge theory, if you like. Okay, and this has been realized in the fractional quantum Hall effect. So this is, I won't go into details, but this is an actual experiment where you can change the magnetic field and measure this thing called the, this is actually RXX, the resistivity. There are these zero resistivity regions where you get new states. This is fractional quantum Hall state, 1/3, where you have a realization of these non-trivial fractional statistics where this angle turns out to be 2 pi over 3. Okay, so it's 1/3 of the statistics of a fermion, if you like, or a boson. And the more direct measurements recently of these fractional statistics. Previously, people knew that to get these states, the only way you could do it is to have fractional statistics. There were general no-go theorems, but now there is a direct measurement where they would put in these particles in a controlled way and see that particles that go around them get this additional phase. Turns out to modulate some electrical signal that you would get in your measurement. Okay, so these abelian anyons are very well known, understood, and known to occur in systems. But there is a further generalization of them. So these are already generalizations of bosons and fermions, but there's a further generalization, which are these amazing things called non-abelian anyons. Okay, so these are again particle excitations. So we have some analog of this toric code state, let's say, some more complicated analog. You make excitations above the ground state, you have particles, and in the case of abelian anyons, you just get the phase. But the generalization of a phase, we have seen before, is to unitary matrices. Okay, so a non-abelian generalization at the mathematical level. But the way this gets implemented is that when you insert these excitations into the ground state, what was previously a unique ground state now develops a degeneracy. Yeah, you get a multiply degenerate ground state, so you get these multiple states. And then when you take one particle around another, these states, they evolve into one another. There's a unitary operator that tells you how these quantum states will evolve. Okay, so these states where I can have this physics realized are called these non-abelian topological phases. Okay, and they are, of course, extremely interesting from a fundamental point of view, but you can also see the analog to doing a quantum gate. You can think of these as qubits. You have multiple anyons put into your system. They're sitting at different places, and somehow the collective state is giving rise to these degenerate states. And then you take one around the other, you implement a unitary operation, which is just like a quantum gate. Okay, so of course, this may seem like the most complicated way to do quantum computing, but it has one big advantage is that everything is, the information is always spread out, so it's naturally resistant to errors. Okay, and that, of course, for regular quantum computers, the coupling to the environment, decoherence is the biggest showstopper. So if you really want to get high quality quantum bits and fault tolerant quantum gates, this is not a bad idea to go in this direction. Yeah.
Out matter or with matter?
So you're looking at this. Yeah, so let me get to that in a second. So, so just to give you again the field theory kind of perspective, this toric code that we talked about was an abelian topological order, and if you look at the fusion rules, you take these particles and combine them together, ask what particle you get, the E and M can combine to get this fermion, we said, but you see that there is a unique outcome. When you fuse two of these particles, you get a unique outcome. These non-abelian topological orders have Also, non-trivial fusion rules. You combine a pair of these particles, you can get more than one possible outcome. So it really depends on the internal state of these particles, what outcome you get. It could also be probabilistic. So here is a simple example, the simplest one, the Ising topological order. It's got 3 particles. You combine 2 of the sigmas, you can either get a 1, the identity, which is going back to the vacuum, or you could get F, which is a third particle in this theory. And this is another kind of topological order, non-abelian topological order, called the Fibonacci topological order. It has only 2 particles, the 1 and the tau. Okay, so this kind of makes the point that these non-abelian topological orders, they can be very simple in their description. It's like this one non-trivial particle. And the rule for fusing to itself, which is the only fusion rule there is you can either get the vacuum or you can get back this particle. Okay, so the rules of the game are very simple, but this turns out to be extremely complex state and very hard to create. Yeah.
Naive question. So what are the states, you said it, but I missed it. What are the states on which the unitary is acting?
Yeah, so, let's, just to be precise, let's imagine this system is on a sphere. So when you have this topological order on a sphere, there is no degeneracy, unique ground state. Now I go and create 2 excitations, let's say of these sigmas. So I put in an energy and locally and I create 2 of these excitations. And now what I discover is that the ground state is no longer unique. It actually has some degeneracy. You can have 2 different ground states that are compatible with having these excitations.
But what does it mean? You already have the excitation. So what does it mean to have now degenerate ground states? There was a unique ground state and now you have an excited state.
Yeah, okay, so in the space of 2 excitations, with that restriction, look at the lowest energy state. So maybe that's your confusion. That's not really the ground state, it's actually excited state.
Okay, yeah. But when you have these 2 sigmas, that means you're in some different super selection sector or something.
Yes,
so
yeah. And that super selection sector there are multiple quantum states corresponding to that. Okay. And you can move through these quantum states simply by moving those sigmas around each other.
Okay.
And then you can investigate which one you're in by bringing those sigmas together and fusing them. Mm-hmm. And if you get 1, that means you are in the 1 state, and if you get F, which is another excitation, you're in the F state. So you can collapse these waveforms. You can actually figure out which state you're in by doing this kind of process.
When you say that this is a different super selection sector, that means that when you have these 2 sigmas and the other state that you have F, they have the same energy?
Yeah, that's right, yeah. Of course, when you move these things, you bring them close, you could change the energy. But it's not, you can also go back to the ground state. In that case, the 2 sigmas, this is an excited state. Then you go back to the ground state, that's the identity. You have to give up the energy somewhere. But it's like you had a particle-antiparticle pair and you fuse it and you go back to the vacuum. You have to carry out the energy somewhere. But you're back in the vacuum, or you could get into a different state where you have another particle sitting there, but it's of a different kind from the ones that you fused. So these particles in this picture of the strings, they're like the endpoints of the strings. But these strings have multiple colors. This is more complicated than the strings that I talked about. Yeah. So I'll give you a more pictorial example of not quite this topological order, but of something else.
Sorry I think I'm still not getting something. So you said if the state with 2 sigmas is in a different super selection sector, then how can you get 1 from it? Because the 1 was in a different sector, right? Naively.
So okay, that's a good question. So you can create these 2 sigmas from the 1. It's like creating a particle-antiparticle pair. So maybe I should not say different super selection sector. If it's different super selection sector, you can never go to the 1. That's your point, right?
But then what are those degenerate states then? You were saying they're the lowest energy states with those 2 sigmas there.
Yeah, so let me say I look at a situation where I guarantee for you that there are 2 sigmas somewhere in my system, and they're far away from each other. Mm-hmm. So it's important they are far away from each other, because if they get very close, you cannot really tell the difference between 2 sigmas and, for example, the identity. Right? So let's work in the configuration where there are 2 sigmas far away from each other. There's a a natural scale in this problem. If you do quantum Hall, there's something called magnetic length and all that. So there's a precise notion in which you are very far away from each other. Now, regardless of where the two sigmas are, the state is degenerate, right? You're just referring to it by the fact that you have two sigmas. And then, if I did this for abelian anyons, so let me think of a contraster to this case. I tell you that there is one open string and one long open string. So there are two E particles. And I can ask how many quantum states do I have if I fix the location of those two E particles. And there's only one state. It's the one where you have that string. There's one minimum energy state where you have that string, and everything else is closed loops. But if you do this for sigmas, you will have two candidate quantum states. That's kind of the distinction.
Okay, thanks.
Yeah.
So for this sigma cross sigma equals 1 plus f, do you mean the super selection sector in by means of direct sum of these two states?
Yes. Yeah.
Not the superposition.
Well, when you actually do the fusion of these two, so if you think of it as physically, you take these two sigmas and you fuse them, you either get the 1 or you get the f. You don't get a quantum superposition of them.
Okay, so it's different from the degenerate ground state that you showed them before, which like where you wrote as a superposition on a bunch of different loops.
Yeah, this is the excitation of that state. Yeah.
Thank you.
Okay, and in terms of quantum field theory, these are the kind of, if you're more familiar with Chern-Simons theories, this Ising topological order is related to this SU2 level 2, Chern-Simons theory, and this Fibonacci is related to SU2 level 3. They're not exactly the same. There are some differences. There are more particles over here, but they contain these kind of topological orders. And another way to think about them is in terms of Higgs. You start with a gauge theory, which could be abelian or non-abelian, a Lie group, and then you have a Higgs condensate that ends up giving you these states. Okay, so I won't spend too much time. There are, people have heard about Majorana fermions, may have also heard about 1D realizations of them at the ends of quantum wires. So there's also a notion of non-abelian defects. They don't quite have the same freedom as particles, so we'll be really interested in states where the particle-like excitations are non-abelian. Okay, but this is just to connect up with other work that people are thinking about, trying to make non-abelian defects, which are again useful for these fault-tolerant quantum computing. Okay, so just a very small word about motivation. Why study these non-abelian topological orders? I mentioned one, which is going towards these fault-tolerant quantum computing, a very distant goal. But I think it's fueled a lot of interest in this area. Another thing that we realized as we worked more on this project is that non-abelian topological order is actually quite different from the abelian variety. In fact, what I feel now is that it's about as different from the abelian ones as these abelian states are from just plain vanilla short-range entangled phases. Again, they're also very hard to realize and probe. In these quantum Hall states, there are many, many examples of the abelian topological orders, literally like dozens or even 50 different states that have been observed. There are just two candidates for the non-abelian states. And even that we're not completely sure. There is a fraction of 5/2, which is very unusual from when it was first discovered, the only one which had an even denominator. Everything else would have odd denominator. This was already suspicious, and the first topological order I talked about, the Ising topological order, is related to the most compelling proposal for this particular state, but again, it's not fully experimentally proved. Yeah, this one you mean?
Defect. So I thought there's no topological order in 1D. So this is So this is like sort of more closer to that integer, like symmetry.
Yes, exactly. Yeah. So the endpoint of this 1D chain could have, again, edge state could have a Majorana 0 mode, but it cannot move. Obviously it's at the end, right? It's not a true particle. It's just a point at which you get, a configuration that has some of the properties of these non-abelian anyons, but not all of them. It has some subset. It kind of has the fusion rules, if you like, but not more than that. It does not have, for example, what people call a topological spin and things like that.
But the quantum error correction properties are still, you could build a...
Yes, yes.
That's surprising, okay.
Yeah, but it's restricted. So, if you had defects creating your quantum bits, you can ask what are the kinds of gates that I can apply by doing these kind of protected operations. And, for this particular topological order, it's only the Clifford operations. So it's a subset of the quantum gates you can apply. But with the more general non-abelian topological phase, you could potentially get any, any quantum gate. So here, this particular topological order only allows you icing, and that's like the Majorana's zero mode. But this Fibonacci over here actually allows for universal quantum computing. But there is no, as far as I know, there's no defect analog of this Fibonacci topological order.
Thank you.
Okay, so these things are hard to create. That's why we thought it may be helpful to try to create it on these quantum devices. And our approach is really to extend what we had before, the toric code, which is a abelian topological order. It had the E particle, the end of the line, the magnetic excitation, and the dion. We wanted to extend this by the following analogy. So the toric code is really can be thought of as a gauge theory, where the group is really Z2, the simplest possible group you could have, and Z2 is an abelian group. Now, if you replace that abelian group by a non-abelian group, again, a discrete finite non-abelian group, one of the simplest such things is D4, which is the symmetry of a square. And if you're able to take this group and actually gauge it, you would get a non-abelian gauge theory. And now the excitations would be, again, you would have some analog of the magnetic excitation. In this particular case, it's really the conjugacy classes of the group. There are 4 of them corresponding to different kinds of symmetries of the square. The analog of the electric charge are really the irreducible representations of this group. And as everyone who's learned group theory knows, the number of these is the same as the number of conjugacy classes. Although there's no one-to-one map, miraculously the numbers turn out to line up. So there are also 4 analogs of electric charge. And finally, there are dions. You can combine these two just like we did over here. And the way you combine them is a little more complicated, but ultimately you get 22 excitations. Okay, it looks complicated, but it turns out there's some intrinsic simplicity which will allow us to build this particular D4 topological order. Okay, you can also think of getting these more conventional particle physics approach. You start with some U1 gauge theory and you have a charge 2 matter field and you Higgs it. You can get the Z2 toric code or the Z2 gauge theory. Similarly, if you started with an SO3 non-abelian gauge theory, there's a particular kind of Higgs. I don't know exactly what it is, but some combination of Higgs fields that will end up giving you invariant subgroup being D4, and that will end up giving you the D4 topological order that we'll talk about. Sometimes it's called the quantum double of D4, so D of D4.
Ions, you mean these are genuine bound states?
Yeah.
And the fact that there are only 13 of them is some dynamical question that you have to...
No, it's a group theoretic problem you have to solve.
Okay.
So there is no dynamics in this. So we're just doing what are all the distinct, excitations of this theory. What are the different anyons in this theory? So you might say, oh, let me just pick any random irrep and combine it with one of these conjugacy classes. But because these are non-abelian, you cannot do that. What you need to do is actually pick a conjugacy class, pick an element in the conjugacy class, and look at the subgroup that leaves that element invariant. So you get some subgroup, and then you look at the irreps of that subgroup. Those are the charges that can be combined with this particular flux to create a dion.
But why is it that the dynamics is, because the statement about whether it's a bound state is a dynamical question, right? Why is it purely given by group theory? I'm just a little confused by, then why can't you,
so you're in a particular theory, it may be that one or the other of these are, lower in energy. So in that sense, you may not have a bound state.
Okay.
Right?
So then in a particular theory, not all of these may be realized as single particle excitations.
Yes. Yeah.
Okay.
Yeah, that's right, yeah. But if I change the theory, I can get them, all to be...
all of them to be single particle
yes,
states.
yeah.
In a particular theory, if you try to make two of these interactive to produce others.
Yes, but it'll sort of be closed, right? This is kind of the entire...
So this is closed, right?
Yeah,
right,
yeah.
But you're discussing a situation with Rajesh, I thought, where you don't realize all of them. If you took a smaller group, it wouldn't be closed, right? If you took a smaller set.
Yes, that's right, yeah.
But then how could you have theories where you don't realize all of them? Then you have to realize all of them, right? If you have the symmetry.
I think Raju is asking a question about dynamics.
So whether there's a Hamiltonian, depending on the Hamiltonian, you may or may not have states with that quantum number, those quantum numbers to be bound states. It may be that states with those quantum numbers are just multi-particle states.
Yeah, and which combination, and it could be that F is the lowest energy, and you can create an E, but if you create an M, it falls apart into an E and an F. But that's a dynamical question. But, for example, this number over here is very important. Even if you have no excitations, let's say you just have the ground states on a torus. You ask how many ground states there are, this is actually the number that controls that. So there's, yeah. So even over here, you'd say it's 3, right, rather than 4. But you always add the vacuum as a trivial state, yeah. So all in all, the number of, I shouldn't have said total, I should say the total number of ground states, yeah. The total number of particles, including the trivial one, is 1 plus all of these.
Sorry, in the context of these lattice models, can I think of this Higgsing you're talking about as adding a term to the Hamiltonian that penalizes having charges? Is that?
Usually it's penalizing some fluxes, right? Because you condense the Higgs particle, and then there are certain fluxes that it's happy with. Those are like vortices. So you can think of it like a superconductor, some kind of complicated superconductor where you had some non-abelian gauge theory, then you condense some Higgs field. So you broke down that gauge group. And now you have particle-like excitations, which have short-range interactions now because of the Higgs field. And then you have fluxes, superconducting vortices that also have short-range interactions. And you can think of those fluxes as these conjugacy classes, and these electric excitations as different representations of the gauge group that survive this Higgsing. Yeah, so this number will be important in how many ground states you have on the torus. Okay, so this, in the last 20 minutes, let me tell you very quickly how. That's fine, actually. How you can try to prepare quantum states using measurement and then the experimental realization of this protocol. Okay, so how can you create entanglement using measurement? This sounds completely backwards because when you go and measure a qubit, you actually know what it is. You actually disentangle it from the rest of its environment. But what the kind of measurements we're going to be interested in are not things that completely pin down your quantum state. Instead, we'll do some sort of partial measurement. We'll measure only part of the information, and what gets left behind is a quantum state which has some of the, can actually have certain quality of entanglement that we want. Okay, so here's an example of a non-entangled state, a product state. Both spins are up. This is the usual Bell pair, so it's maximally entangled. And one way to think about the state is that, I want to satisfy the constraint that the product of sigma z is 1. And, I want the maximal superposition consistent with that product being 1. Okay, that's this Bell state. Now, here's another example of a state where, although it has these many terms, it's actually unentangled. It's really a product state with both of the spins being in the x direction. Okay, so let's say I start with this particular state, and then I do a measurement. Okay, I go and measure the product of sigma c. Okay, and let's say the measurement outcome is +1. Okay, if the measurement outcome is +1, I know that the final state I get is exactly this one over here. Okay, so you'll be in the branch where the up down and the down up are not realized, but you have no idea whether you got up or down down. Okay, so you end up starting with this particular product state, doing a measurement, and ending in the Bell state. So you created an entangled state by doing this measurement. Okay, now of course a key point over here is that if the measurement outcome is +1, do you get this? So if you want to prepare the state consistently, you just did measurements randomly, you would get ±1. You would only pick those cases where you got +1. Okay, so that's called post-selection. Now, post-selection is fine when you only have these 2 qubits, but it's kind of a wasteful process, right? Half the time you throw away your state. And we're going to go to the many-body context where it would be real death to do this post-selection. You will have exponentially small yield when you do this for large number of qubits. So you don't want to do post-selection. You actually want to utilize the measurement outcome that you get. So what you can do is if you got the measurement outcome +1 and you're trying to target this particular state, you do nothing. But if you got the measurement outcome -1, what you can do is you can go and flip the spin. Okay, you can go and flip the first spin. So if you got -1, you're in the branch up, down, plus down, up. Go and flip the first spin, apply sigma x to it. You'll end up getting this Bell state again. Okay, so there is a way to deterministically prepare the Bell state using measurement, but you need to know the measurement outcome. You need to know whether you're +1 or -1. And then based on the result of the measurement outcome, you should have the ability to perform a unitary operation. Okay, so that ability is called feed forward. The ability to measure a subset of your qubits, or some partial information about your qubit mid-circuit, and then based on the outcome of the measurement, you apply a unitary of your choice. So if you have this kind of ability, then without any wastage, you can prepare a quantum state of your liking. So M is the outcome, the measurement outcome. If it is plus, let me say M is 0, and if it is, I didn't define that, sorry. Yeah, but okay, so at this level, one may wonder, why are you doing this, right? There are simpler ways of getting the Bell state by doing C0 gates, as you said. But we'll see in a second that it actually has a big advantage if you go to the many-body context. Okay, so so let's say we want to prepare topological order. Okay, so it's easy to show that if you're doing just unitary circuits, if you start at the product state, you do a unitary circuit to get to the toric code, let's say, or turns out any topological order, you need a linear depth circuit. And people have actually done this experiment using unitary circuits to create this toric code. And you can kind of see the numbers over here tell you the value of the stabilizer, the product of sigma x or the product of sigma z. If they were exactly 1, means you got perfect preparation. They're slightly below 1, but they're close. Okay, this was the Google experiment. Used unitary preparation to do this, but it's a very deep circuit. And deep circuits are really the hard thing for these quantum computers to handle, because you keep doing these gates, you accumulate errors, and finally they die. Question is, can you prepare the state more quickly if you are allowed to do measurement? And it turns out that if you have using measurement of exactly the kind of thing that I talked about before, you can speed up this process where you can have the depth of preparation for the circuit is actually independent of the system size. So it's a shallow circuit that can create the toric code if you are allowed to use measurement. And one or two other things which we'll talk about, it's this feed-forward kind of ability. And actually, this was an experiment we did with Quantinium, creating the toric code using this measurement-aided preparation, and you can see it's very good. Stabilizers are close to 1. Yeah.
So are your measurements k-local here?
Yes, yes. Yeah. You measure the stabilizers, basically. You measure the product of sigma z and the product of sigma x.
But only on a few qubits?
4 qubits at a time.
4 at a time.
Yeah. I mean, in practice, you don't actually measure 4 qubits simultaneously. You have an ancilla qubit. You bring in another qubit, you do some entangling gates so that the state of the ancilla is entangled with the state of the 4 qubits. You go and measure the ancilla. But the way you set it up is that once you measure the ancilla, you know exactly what the stabilizer is. So it gives you that information. But that's more a practical kind of thing. Yeah, so let me tell you how you create this toric code. This sort of amazing result that, which was known actually for a couple of decades using just finite depth quantum circuit. Yeah. Yeah, those are the 2 different kinds of stabilizers. So we had product of sigma z and product of sigma x. This one is just random. Yeah, it's maybe they're different gates. I think they're like different unitaries. But I stole this from the. I didn't make it myself.
So, since your strategy is to measure the stabilizer, doesn't that mean that effectively you're only doing different gates, finding state that is an eigenstate of all the stabilizers?
Yeah, so this, for the toric code, that's exactly what it will be. But then we'll talk about non-abelian, where it's a little more complicated. But let's do that in stages. Let's understand the simpler one that was.
One more question. This is sensitive to the initial state. So the initial state had to be carefully prepared to be.
No, it's going to be just a product state. So state preparation, the rules of the game are you start with the product state.
Product state, right? Where everything was 1 plus down by square root 2.
Yes, but that is very easy to prepare, yeah. If it's something else, I'll apply one gate to get it into that state, yeah. But you need a predetermined starting state. Let's say it's all sigma x equal to +1 everywhere. Okay, so the way you do it is the following. It's very easy to understand. You're trying to get the ground state where this product of sigma z and the product of sigma x are both 1. Okay, so now those are the two stabilizers. So we said that this product of sigma z is like saying there are no E anyons.
Ashvin? Sorry, I have a question. So is this only true for stabilizer states, or could you use a similar protocol for non-stabilizer or this high magic states?
So the example I'll give you for this non-abelian thing, we're also going to go and measure stabilizers. But actually, it turns out those stabilizers don't commute. So it's somewhat more general than regular stabilizers. So you can ask what are the most general kinds of states you can prepare using this protocol. And we have an answer for that, but it's not a very simple answer. The answer is something like the group that you can gauge has to be solvable. But let's get to that in the discussion. So it's some subset of non-abelian states that you can create efficiently. But the intuition for that is yeah, we can talk about that. But let's first understand this, where everything is commuting stabilizers. Even there, how do you create a toric code state in a constant depth? And the way you do that is, let's say you start with sigma x everywhere, eigenstate everywhere. So in some sense, by this initial state, you're already guaranteed to have this particular stabilizer being satisfied. Okay, if sigma x is +1 everywhere, product of sigma x is also satisfied. The problem is with the other stabilizer, product of sigma z. Okay, so what you go and do is you go and measure this product of sigma z from starting with this product state. Now, in the very unlikely event that everything gives you +1, you have the toric code. Okay, so you already have, previously you got product sigma x equal to 1, product sigma z turned out to be all equal to 1. The two things commute, so you're not affecting what the product sigma x was when you did the sigma z, product sigma z measurement. So you ended up with the Z2 toric code. Of course, this is exponentially rare for this to happen. What about the more generic instance where you get some +1s and some -1s? Okay, the physical picture of getting a -1 over here, we said, is actually having E anyon. A particle is sitting somewhere in your system. Okay, so the typical measurement will give you a bunch of +1s, everything is good, but some of them are -1s and you have the E particles. Okay, so then there is a final cleanup step. You need to, after the measurement, you know the measurement outcome, you know exactly where these E anyons are. You need to kind of bring them together and fuse them and get rid of them. You bring two E anyons together, you fuse them into the vacuum.
You get a lot of these anyons, right?
Yeah,
half of them will be anyons.
Half the sites have these E anyons.
So the cleanup step is doing a lot of work.
The
cleanup step is doing a lot of work.
Turns out you can do it in one layer alone. You can do it in a single step. Okay, so what you do is one canonical way is you pick a central site and you bring all the anyons to that site. And you can show that you can do that in a single layer of unitaries. So regardless of, and actually it's very easy to see, I'll show that in the next slide. There's a very efficient cleanup step which gives you a finite depth, which ends up preparing the Z2 toric code. Again, this goes back to work of early error correction work several decades back. Okay, so in some sense, there is a point where you actually have linear in size scaling. It's sort of hidden in this. The place where it appears is that you really need to know where all these anyons are after you do the measurement. Okay, so in other words, if you're collecting information from the edges of your system, you need classical information to travel from there to a central point, let's say. So you're limited by the speed of light. So in that sense, it is still scaling linearly with the size of the system. Okay, but who cares about that, right? In any real, any quantum computing platform, those kind of overheads are unimportant. It's really the number of quantum gates that you have to apply. That's really the linear overhead you care about. But in principle, it does have this linearity in the limited by the speed of light, yeah.
It does look like measurement-based quantum computing. Can you comment on that?
Say it again?
This procedure does look like measurement-based quantum computing.
There are some analogs, and I think measurement-based quantum computing is due to these Rosendorf and Bravi, so similar.
But how is it similar and different? Because it's a little bit, yeah.
Maybe we should talk about it later, yeah.
Don't we start with a highly entangled state there and use the entanglement as a reason?
Yes.
Here you're starting with a product state somehow.
Yeah, that's a good way to say it, yeah. Although sometimes there you start with SPT states, which can be prepared in finite depth. But okay, cluster states they're entangled in a particular way, but not in the same way as these topologically ordered phases. But there is a place we use cluster state, this measurement that you do for the ancilla, the thing that transfers the entanglement from the stabilizer to the ancilla. The circuit that you use is the one that prepares the cluster state. So yeah. But okay, just to make sure you understand this cleanup step, because it's very important, let's say I got two of these E anyons. These are two places where the measurement outcome was minus rather than plus, and I want to fix it. Okay, and the way I can do it is I just apply these X's on this line, connecting them, and that will get rid of the anyons. So when I see this configuration of E particles, if you like, I can drag them all to a central site. All of these X's commute, so it's just a single layer where you apply the X's, and you're guaranteed to have an even number of them, so they're all gone at the end of this process. Okay, so for abelian, you can extend this to any abelian topological order, and you can, basically it's a very efficient way of creating any abelian topological order measurement. Yeah.
Non-intersecting, many of them, you need non-intersecting.
They can intersect, in which case the X's will cancel out. You don't have to do anything on those bonds.
And that doesn't.
Yeah. So finally you get you do some sort of compiling of all of these strings, and then you figure out which bonds you actually have to apply it on. Many of them may cancel out because different strings are, and there may be an efficient way to do it where you apply the minimum number. Yeah, but here we're only thinking about a number of layers. And then it doesn't matter. You can do the most inefficient thing you want, and it's single layer. Okay, so the question is, why can't we do exactly the same thing to prepare non-abelian topological order? Okay, so you imagine some Hamiltonian. You start with some product state. You go and measure whether there are non-abelian anyons. And then you find some of them, and then you do cleanup, and you get non-abelian topological order. Okay, but what turns out that this naive approach does not work for non-abelian anyons. And it turns out this cleanup step is in general very complex. And it's related to it's a very intrinsic property of non-abelian anyons. So there was a question before about what toric code Hamiltonian should I take? Should it all be -1 or? Actually, it turns out you can take any coefficient for the toric code Hamiltonian. If you have a positive coefficient, you will have an anyon. But somewhat it's a question of your definition, what is trivial and what is the anyon. Okay, the excited states of a toric code where you have some anyon somewhere and so on look a lot like the ground state. It's very different for non-abelian anyons. As soon as you put in a non-abelian anyon, it has a degeneracy associated with it. So it looks very different. And you cannot have the same kind of, that's sort of related to the fact that the cleanup is going to be very hard. Typically, the cleanup itself will scale with the separation between these non-abelian anyons. So since they're typically separated by half the system size, it again goes back to being linear depth. And then you could have just done the linear depth unitary circuit. Okay, so that was kind of the status when we came to it. But what we found is that for some non-abelian anyons, you can actually create it without ever creating non-abelian anyons in the process. And for that subset, if you tune your preparation in the right way, you can actually use measurements to speed up your non-abelian state preparation. Okay, so I'll just give you an example of such a construction. So here is a more complicated way of creating the Z2 toric code. I've changed the lattice. It's now a Kagame lattice. And I also have 3 different colors. So we're actually going to get 3 different Z2 toric codes. I'll call that Z2 cubed. And you have stabilizers, products of sigma Z, these 3 Z's over here, of say for the red color. And then you have product of sigma x on some 6 body operator. If you do all of these, if you place all of these stabilizers in the +1 state, you just get 3 copies of the Z2 toric code. Okay, so this is just a loop model, if you like, again. This is what the stabilizers look like. And this is basically a loop soup with 3 different colors. And you have 3 E particles, 3 M particles, and they have all these simple fusion rules. Okay, now the one change we're going to make to this quantum superposition is every time there's a configuration like this, 2 of the green and blue intersect inside a there's a red, green and red intersect inside a blue hexagon. I'm going to put a minus sign in the wave function. So the amplitude is exactly the same for this superposition of loops, but when I have configurations like this, I'm going to put a minus sign. Okay, this state, it seems like a small modification of the Z2 cube state, but it turns out that this state is actually a non-abelian state. And it's really the quantum double, this D4 quantum double, where some of the fusion rules are trivial, but some of the other fusion rules, actually, you can see there are many different outcomes. This is a non-trivial fusion outcome, these tell you that this is a non-abelian state. Okay, so this builds on a lot of work on symmetry-protected topological phases and connection to gauge theories and so on. But you'll just have to accept this particular idea. And the question is, how do we twist that toric code to get this additional phase factor? Okay, so I'm already at noon. So what do we do?
Do you feel that 10 minutes, 15 minutes?
Yeah, maybe 10. Yeah, I'll try to finish in 10 minutes. Okay, so it turns out the Hamiltonian that will give you this twist looks very much like the old one. It's again the stabilizers, product of z's. But this one previously, which was just a product of x, is now going to be dressed with some other operators over here. It's called control z, but you can just think of it as product of these 2 sigma z's over here. And then there's some additional factors to make up this control z. So if I have this, if I can find the ground state of this Hamiltonian, it'll give me exactly that superposition of loops with that relative minus sign. Okay, so these are stabilizers. So there's a question whether these stabilizers. So you want to create them to be both +1s. The A's and B's commute, but you can see that the A's do not commute with one another. Okay, so in that sense, it's not a commuting stabilizer Hamiltonian. It's a little more complicated. But if you live in the particular subspace where all the B's are equal to 1, project into that subspace, then you can show that all these A's commute. Okay, so that's what we're going to do. We're going to go first into that subspace, and then the fact that these things all commute will be similar to what we have done in these previous cases. Okay, so rather than telling you, going through a lot of that theory, let me just talk about the experimental realization and, yeah.
So just to understand, so now you're taking a different Hamiltonian in which the control Z is that phase.
Yes.
This thing, and or rather, it is the Hamiltonian which has as its ground state that twisted sort of sum. Okay.
Yeah.
And then you're saying because you have changed it, the A's no longer commute, but on this subspace.
Yeah. So all of these you have to just believe me, right? That. But there's a way. This is not sort of a. It didn't come out of the blue. We had a way to start with the Z2 cubed toric code, and then there's sort of this digraph-Witten twist that you can make. And by now we understand very well how to do that at the lattice level. What is the unitary operator you need? How do you conjugate the original terms in order to end up over here?
I mean, you mentioned
yes,
this digraph.
Yes, yeah. So if you have 3 of these, Z2 gauge theories, you can write down a discrete Chern-Simons term. So let's say the 3 discrete gauge theories are A1, A2, A3. You can do A1, wedge A2, wedge A3. Of course, for a continuous gauge group, that's not gauge invariant, but for Z2 valued gauge fields, it is. And that exactly gives you this twist. Yeah, so let me just talk about the experimental realization, and you'll see some of these more conceptual questions showing up. So we did it on this particular machine, which was the only one that allows you to do feed forward. You go and measure a subset of the qubits and then act with unitaries based on the outcome. So it has only 32 qubits, but that turns out to be enough for us. And one of the nice things, it has very good fidelity. So this is how good the single qubit and 2 qubit gates are. So only 2 in 1,000 times do you get the wrong gate applied. And they have this mid-circuit measurement with conditional logic. They also have this all-to-all connectivity. So the way this thing works is your qubits are actually in one dimension. They live on this racetrack. But when they live on this racetrack, they simply do not talk to each other. They're completely isolated. And the dimensionality of the storage does not really matter. The way you actually create entanglement between qubits is you bring them to these regions where you bring 2 qubits together, let's say, and then you shoot laser pulses and you apply a quantum gate. You can also measure them in these regions. So you design the geometry yourself. You pick 2 qubits and you entangle them. You move them back, and then you can take another pair and entangle them and so on. And that actually gives you the geometry of your lattice. It's really by design that you end up creating the geometry. And for example, we can do periodic boundary conditions because you can select any geometry you like, apply the gates in order to get these periodic you can do things more complicated as well. Okay, so that's a minor point. It's not very important for us, but it helps us work with small systems without any edges. Okay, so this is the way in which we do the ground state preparation. You do some.
A little bit more about the gates. So the gates are not phonons; they're external lasers.
They're lasers, yeah.
But lasers decouple external to one of the ions. How do you couple an ion to an ion with a laser?
That's a good question. The only thing I know about this is it's called a Sorensen-Moller gate. Does that mean something to you? Yeah. So the quantum bits themselves are hyperfine states. And there is a way to do 2 qubit gates using lasers. But I've not been able to dig into the details of how exactly they do that. But it's different. There are actually 2 different architectures for ions. One is using phonons, the Zoller, Sirac kind of way of doing it, and this is the other way. The advantage of this is that it's literally by picking ions, you select which ones on which you apply the gates. And I think this kind of conditional logic is specific to this implementation of ions. Okay, so here the ground state preparation, I won't go into the details. It involves some unitaries. The 2 important things are that we have measurement over here, and based on the outcome of measurement, you do a correction, a cleanup step. And the way this whole thing has been choreographed is such that when you make a measurement and you get an error in the sense you get the wrong value of the stabilizer, the only excitations you create are abelian excitations. Okay, so this is a topological order that has both non-abelian and abelian excitations. Some excitations have trivial fusion rules. In this process, when you do the measurement in the ground state, you sometimes get defects, but those defects are only the abelian excitations. Okay, and by cleaning those up, which is easy, for example, over here, you just apply sigma z on these 2 things. You can prepare the non-abelian topological order. Okay, the other thing that's important over here is that here there's a gate which is not a Clifford gate. And that is completely crucial if you want to create this non-abelian topological phase. Yeah, and then you can go, after this process, you can go and measure these stabilizers and see how well you've done. Okay, if they're all +1, then you're perfect. You're never really +1, but what do you get? And it turns out it's pretty good. Okay, the stabilizers that they measured at the end of the day are pretty good. I think the worst one may be 0.88. And based on these values of stabilizers, you can estimate that the fidelity preparing this particular ground state is greater than 75%, which per site is about 98%. Okay, so it's pretty good fidelity. And basically this shows that you successfully managed to prepare the state on, okay, these are 27 qubits. It's a 3x3 system, so not that big. But we'll say it's big enough for our purposes. We can do everything we want on this particular system size. Okay, so in a way, it's a waste of a quantum computer because you can find this ground state with pencil and paper, right? But on the other hand, the quantum computer actually creates the state. Those 27 qubits are actually creating the ground state for a 3x3 lattice of a non-abelian topological order. So in some sense, you actually have the wave function stored in a quantum system. Okay, so you can also confirm the fusion rules. So you can, for example, create excitations, violate these stabilizers, and then bring them together and see that they obey these fusion rules. I won't go into the details because I'm running out of time. Sorry, this is sort of a animation. You can actually check that you have all the different ground states. So you can create all quantum states that have stabilizer values +1. And it turns out it's not unique. There are actually exactly 22 of them. And that 22 is the number of anyons in your system. There's a result that degeneracy on the torus is equal to the number of anyons in your topological order.
The Hilbert space? How do you measure experimentally the dimension? I mean, the 22 states, but I mean, it's a linear space, right? So there are actually infinite number of
Yes,
states.
that's right. So what you do is the stabilizers, they're all these local things. So you can show that, let's say you measure all of the stabilizers and you get +1. How do you know there are two states for which that happens? How do you know they're distinct? It turns out there are these loop operators. They're basically Wilson loop operators that span the torus, and they're different for these two states. So you can show that there are 22 different states that have exactly the same stabilizer values, but distinct values for these loop operators.
And you can measure and show that there's really a 22-dimensional space.
That's right. Yeah. Now, one thing that was a bit confusing for us, so these loop operators look something like that. So these are products of some Paulis along this or that. If you do something naive, the number of loop operators that you can write down is the same as 3 copies of the toric code. Okay, so you would have thought that the number of anyons over here, as labeled by the loop operators, is the same as in the toric code. Toric code, we know on the torus there are 4 of them. So if you have 3 copies, there would be 4 cubed, there would be 64. But here we only get 22 of them. And so what is the 64 minus 22? Where are they? It turns out all of those are actually excited states for this non-abelian topological order. Okay, so for those, the 64 minus 22, actually some of the stabilizers light up. These local operators light up, and they're not ground states. They're actually excited states. But the interesting thing about them are they're actually excited states with a single stabilizer that is violated. Okay, so a single stabilizer is violated. What we'd say is that there is a single anyon. So our general feeling is that when you create anyons, you always create them in pairs. You create a particle and antiparticle pair. But actually, this intuition is incorrect when you have non-abelian topological order. So if you have a non-abelian state on the torus, you're actually allowed to create a single anyon excitation as labeled by these stabilizers. And in fact, it's crucial you have these. This is what gives you the difference between the number of naive ground states and the number you actually end up with.
The non-abelian Gauss law still, right? So how does this is somehow a state which is compatible with that non-abelian Gauss law?
Yeah, that is kind of the thing that is a bit disturbing. If you have a source, where is it going? But it's non-abelian, so that is kind of it's more complicated. And actually, there's something we knew before. After this work, I realized I knew this before for the Ising topological order. So for the Ising topological order, you can have flux excitations. The boundary conditions could be periodic and periodic, and one of them could be antiperiodic, but they cannot both be antiperiodic. If they're both antiperiodic, you can show that there's a fermion in the ground state. So that's not one of the ground states. So you have the naive counting of 4 for the ground states, but one of them is excluded when you have antiperiodic for both of these cycles, because it actually is an excited state. And it has a single fermion associated with it. So this is actually not specific to this D4. It occurs in much well-known non-abelian topological orders. Yeah, but the fact you have stabilizer Hamiltonian very clearly allows you to define this as an excited state. And it has a single place where it's violated, so it's a single anyon excited state. Okay, so another nice thing about non-abelian excitations is that they're much better at doing knot theory compared to abelian anyons. So abelian anyons, the only kind of knots, so the knots over here, as you know, is the space-time configuration of these particles. So You read this as a function of time, you create a E particle-antiparticle pair, create M and particle-antiparticle pair, you braid them, and then you fuse them back to the vacuum. There's a relative minus sign for this braiding. So it can detect this kind of knot, if you like. So abelian anyons can detect any kind of linking. If you have a knot which has linking, these abelian anyons can detect them, but there are actually knots that have no linking at all. So an example is this Borromean ring. So there are these 3 colored loops, and if you cut any one of these loops, you can show that you can detach the other 2. Okay, so if you cut the blue loop, you can detach the red from the green. And so there is no abelian anyon that can detect this kind of knot. Okay? But this non-abelian thing can. So it turns out for the non-abelian topological order, there are 3 colors of excitations corresponding to these loops. If you send them through this particular space-time configuration, you expect to get a -1. Okay? And this is something that can be measured. I won't go into the details of how it's measured, but you expect -1, and the experimental value is something like this, which is pretty close to what we expect. Okay, so I'm almost out of time. So this, if you like, this is another way to confirm non-abelian topological order, and that was really the hardest experiment that they did. Okay, so I showed you how you can construct these non-abelian topological orders in a fast way using measurement. And this route was actually useful for us because we could create this D4 quantum state on the existing quantum devices, making use of this the speed up. But you can ask, how general is it? What are the, if you think about non-abelian gauge theory got by gauging a particular group, which groups can I actually put through this kind of crank? And it turns out the answer, as far as we can tell, the groups for which we know how to do this are all these solvable groups. Okay, so what is a solvable group? So this comes from Galois theory. So all abelian groups are solvable, but there are non-abelian groups that are solvable as well. And these solvable groups actually first appeared when people were looking at equations, polynomial equations, trying to find an analog of the square root formula, right? And you can do this for the cubic and the quartic, but not for the quintic. And the most general result was obtained by Galois, who showed that with every polynomial, there is certain symmetry. You can permute the roots of the polynomial, but that does not affect the coefficients of the polynomial. So permutation of the roots is a symmetry of the polynomial. And so there's a group associated with each polynomial. And the cases where you can actually write down explicit formula, like the quadratic formula, are ones where the group is a solvable group. Okay, and the first non-solvable group that you have is A5, the permutation of 5 objects, even permutations of 5 objects, which is why the quintic does not have a general formula. Okay, so anyway, there's some weird connection between, sorry? Yeah, you're right. Yeah, good. So S5 is 120, yeah. Yeah, nobody has ever pointed this out before. Thanks, Rajesh. Yeah. Yeah, so there's this weird connection between this Galois theory and what we can do. The solvable groups are the ones where we can arrange the measurement so that you only have abelian anyons, you clean them up, and you keep going, and you end up getting the ground state of these gauged solvable groups. Okay, so let me not...
Is this an empirical observation?
Yes, so right now we have an explicit way of doing any solvable group. We think we have a proof to show that non-solvable groups cannot be made, but it's a physics proof, right? I can tell you what the loophole is. There is a loophole which is you worry that you could create a much more complicated topological order and then reduce to this non-solvable case. For example, in this A5 has no abelian anyons. So our procedure does not work. Our procedure gets its entire strength by doing this measurement, creating abelian anyons and cleaning them up. If you cannot even start doing it, you cannot do anything. So you cannot create A5. Now the worry is you can create something much more complicated than A5 and then reduce down to it. And that we have not been able to eliminate. But I suspect that, it's actually impossible to have a shallow depth preparation of a non-solvable group, but it's not been proved yet. There's no completely satisfactory proof yet. But that's the conjecture, that the others are not, it's not possible to do the others. In the sense that you have finite depth unitaries, measurement, and feed forward. Okay, so let me end over here. Those are all that's actually the experimentalists and the experimental group that we collaborated with. Okay, so let me, stop here. Thank you. I think I said some of them. Okay, so yeah, you can read it. They cannot be efficiently gauged. Yeah, we can gauge it by doing the linear depth process. That is always available to you. The question is, is there a shortcut? Which is where the depth is independent of the system size. Sometimes the shortcut helps you because like on these things, it would have been hard for us to do the unitary one. Sometimes maybe once things get very powerful, maybe you don't need that, I don't know. But it's an interesting question whether there's a shortcut. And for non-solvable, we think there is no shortcut.
Thank you, Ashvin, for the beautiful talk. Any questions? Okay, there were a lot of questions during the talk. So let's thank Ashvin again.